Okay, thank you, Marco. Yeah, I'm going to try and keep it within about 45 minutes to keep as much time as possible for Q&A. What I'll be talking about is a particular type of research collaboration that I think can perhaps really help productive engagement between philosophers and scientists. So it's this idea of an adversarial collaboration. So I will start out with a definition and also contrast it with, I guess, what is a traditional type of collaboration, which I'll call agreement-based collaboration. So broadly defined, an adversarial collaboration is a research collaboration based on disagreement over a theory or an argument or a theorem, depending on what discipline you're working in, which aims to progress towards a resolution. Okay, so that's an adversarial collaboration. To better understand it, it's worth comparing it to, I think, the traditional mode of collaboration, which is agreement-based collaboration. Hard to define something so broad, but here's a definition. It's a research collaboration based on agreement over a theory, argument, or theorem, which aims to test it, defend it, or prove it, depending if it's a theory or an argument or a proof. Okay, so agreement-based collaboration, I'm sure you're all very familiar with. You've got some colleague and you agree on something. Maybe you agree that there's a really good test for some theory that's out there, or maybe you agree on a theory and you want to defend it together. Or maybe if you're a philosopher, you agree that there's some argument that's sound and needs to be defended in the literature. Or perhaps if you're a mathematician, you see that there's something there to be proved and you want to write a paper proving it with someone who agrees with you on that. So that's pretty traditional collaboration. You work together because there's some foundation of agreement that you're building upon. So an adversarial collaboration is kind of the opposite. What grounds an adversarial collaboration is disagreement. Disagreement is what founds and starts the collaboration. Okay, so to further illustrate this concept, let's look at some examples. This, as far as I can tell, is the first ever published explicit adversarial collaboration. If anyone can think of any earlier ones. So this is 1988. Resolving scientific disputes by the joint design of crucial experiments by the antagonists. Okay, so clearly a collaboration based on disagreement via these antagonists. Comes from applied psychology. Psychology and the social sciences is where adversarial collaboration really came and got popular over recent times. And I don't want to go into the actual discipline-specific details of this adversarial collaboration. I'm interested more in the structure. But as you can see from the things that I've highlighted in the abstract, we describe a unique method for, this is actually kind of hard to see, resolving scientific disputes, the joint design of crucial experiments by the antagonists themselves, with the help of a mediator. So this is a common way in which adversarial collaborations can be structured. You have the antagonists, but you also go and find some neutral mediator who perhaps doesn't have a strong view on either of the positions under debate and who can sort of help resolve the dispute. Why do this? You might think, this is difficult, we disagree, but maybe you can think of obvious justifications. And the second thing I've highlighted is a kind of justification for this sort of research. Latham and his colleagues had obtained markedly different results from those obtained by Erez and her colleagues. Okay, so basically what happens in the literature is they're publishing these papers where they are reporting contradictory results. Again, the discipline-specific details don't matter too much to me. The point is, that was the catalyst. It's like, hey, we're getting these results, publishing these papers, we're just getting these different results. What's going on? Well, let's work together, let's figure it out and see what can happen. And this seemed productive, it seemed to work. As I highlight at the end, it was concluded that the differences between Latham and Erez can be explained on the basis of differences in specific procedures. Okay, well, this was worthwhile, it seemed to work. And then they say, and the method used to resolve this dispute should be used by other investigators. So they were putting forward a structure for a certain sort of collaboration, which they think is productive. And they want to say, hey, here's a kind of a template. We think others should use this template because we think this is going to accelerate scientific progress. And I agree. I think many others agree that this is a good way of accelerating scientific progress. Not long after this, the Nobel Prize-winning economist Daniel Kahneman really championed the idea of an adversarial collaboration. And so it got quite popular, at least in the social sciences and psychology. Let me give you one more example. So this is now a contemporary example, a contemporary ongoing example. And it's certainly by far the largest, most widely discussed, and certainly most expensive adversarial collaboration. So now we're moving to neuroscience. This is in neuroscience, and it's an adversarial collaboration between advocates of two different neuroscientific theories of consciousness. Okay, so you've got advocates of one theory, I mean, the details don't matter, integrated information theory versus another global workspace theory. So they get together, but yeah, there's a lot of people on this list. The first thing says Cogitate Consortium. This is just an organization that has well, many labs, but 6 labs that are being used here. And this is part of being a neutral mediator, because they don't want to use the labs of the advocates of these particular theories. They want to be as neutral as possible. So they're using these labs that are, well, owned and run by people that have nothing to do with the defending of these particular theories. But then, yeah, there's all these other people on the list as well, and also a few philosophers. So this is a philosopher science collaboration. You've got Francis Fallon and David Chalmers, for example, as 2 of the philosophers in this group. So part of the motivation for this particular adversarial collaboration is just what's been happening in this particular field over the last decade. So what's been happening in this particular field, the neuroscience of consciousness, is that you have these various different neuroscientific theories all being developed in parallel without any real crosstalk between advocates of these different theories. And the integrated information theory and the global workspace theory, which are the 2 theories being debated here, are just 2 examples among many. And there were actually a lot of meta-studies of a lot of what was being published in this field. And what was found is that, yeah, not a lot of crosstalk, and many advocates of these theories typically just giving post hoc interpretations of data. So this was put forward as a kind of resolution to that problem where we actually pit these theories against each other. Okay, so this one's an ongoing one, and this is a screenshot of just the first set of results that they released. Okay, so that's the basic idea, and that's a couple of examples. What I want to do now is make a distinction between 2 different types of adversarial collaboration: empirical adversarial collaborations and theoretical adversarial collaborations. Okay, so what's an empirical adversarial collaboration? Well, I just gave you 2 examples. So there's a sort of a basic strategy that you can extract from all of these adversarial collaborations that have been conducted so far, or almost all of them. So it starts with this common ground. You know, we begin with this disagreement. We disagree on our theories, but then we get together and we try to agree on something, and we build on this common ground. And so in particular, you come together and you try to think up of a procedure for an experiment that would distinguish between the competing theories. And then you try and figure out what sorts of results would actually cause you to give up your theory. What kinds of results would actually falsify your theories. So you try to agree on that in advance, and usually you have neutral mediators that are helping with this to help keep you honest. And then you go about doing your experiments and then see what happens. Okay, I'll just very briefly mention the way that I've written the basic strategy. It's pretty rough, and there's a lot of room for improvement, and there's a lot of research trying to improve the strategy here. A real quick example is this interesting paper, Accelerating Scientific Progress Through Bayesian Adversarial Collaboration. And so part of what these authors are trying to do is they're trying to improve point 2. What results would falsify the theories? So their work is basically saying, look, I mean, falsification's a little bit too strong. Sometimes falsification's a little bit too hard to come by. Let's instead talk about what kinds of results would decrease our credence in our theories. And okay. Another reason to put that up is it's also another science philosophy collaboration with Jakob Horry in the middle being the philosopher. Okay, so lots of empirical adversarial collaborations that have been done, lots ongoing, and I'm sure lots more to come in the future. What about a theoretical adversarial collaboration? Well, there's certainly a lot of disagreement out there among theoreticians that in many different fields that cannot be so straightly resolved by getting together and coming up with an experiment. But nonetheless, what I want to argue today is that the idea of an adversarial collaboration is a really, really good idea for people in more theoretical domains where experiments are not so easy to come by. Now, so what would be nice is if I could go to the literature, find examples of theoretical collaborations and abstract, again, a strategy, a basic strategy, a template for what to do here. But I didn't really find one. It was hard to find. It was actually really hard to find any theoretical adversarial collaborations at all. Any pointers to any, because I'm still searching lots of different sciences to find them, let me know. But you can perhaps kind of understand why they would be so rare. People don't really want to hold on to give up their theories too quickly, theoreticians in particular. And if you don't have cold, hard empirical evidence that, especially a neutral mediator can point to and say, sorry, you've got to give up your theory. If you don't have that, it's unclear why this would be successful. So it's not clear why a theoretical adversarial collaboration would even be successful. Okay, I want to argue that it can and will, I think, in the future. I think hopefully we'll see more of these in the future. Okay, so that's probably why I could barely find any. But let me just briefly mention what I did find. I found a couple of examples, real briefly, just, okay, here's one from psychology that I found. Okay, so you had two people who had one kind of way of thinking about envy, and then two other researchers had a completely different way of thinking about envy. They call it the dual approach and the unitary approach. Again, never mind the details, the discipline-specific details. It's more the structure that I'm interested in. So what did they do? This wasn't experimental, it was conceptual. They were just conceiving and defining envy in very different ways. And then it was just really, really hard to sort of compare what they were doing, especially in the downstream empirical research. Well, in this paper, which I'm not criticizing, I think, great paper. I'm no expert in this field, but I'm sure it's a great paper. But what they employed was a kind of question and answer strategy. So you look at the paper, 6 questions, and then here's the answers from the 2 groups of antagonists, and that's it. And sort of no real conclusion. There's a very small conclusion at the end, but all they really conclude is we learned a lot from this. And one of the main things we got from this is that we have made some really good collaborations and would like to collaborate with them in the future. Okay, so this is not quite what I'm thinking of. I'm wanting more from a theoretical adversarial collaboration. In fact, what I would say is what they've done here would be step number 1 in a theoretical adversarial collaboration. One other example I found was from philosophy. I really feel like philosophy would be helped by these kinds of collaborations, and so I was a little bit surprised that it was so hard to find. But you have here Lil and Murad with this book, How Philosophers Argue an Adversarial Collaboration on the Russell-Copeson Debate. So I was like, okay, well, that looks perfect. It's all in the title. The Russell-Copeson debate is a debate over the existence of God. But then, okay, you look at the book, and it turns out the authors don't actually disagree on that. One doesn't take Russell's view where the other takes Copeson's view. That's not what this book is about. The Russell-Copeson debate was just a debate, a live debate that was aired in the BBC, I think in the 1940s. But if you teach, especially informal logic, often these are used as examples of argumentation. It's a really nice illustration of just argumentation, never mind the issue of whether God exists. They just nicely illustrate different ways of arguing. And so in an informal logic class, it's a really nice example. So this book is actually more about how to use that debate to teach argumentation. And so they disagree on exactly how to sort of teach argumentation to students and how to think about what you should include in an argument. One thinks they should be more rhetorical, the other thinks they should be more formal logic based. Okay, so that's sort of on the right track, but also, yeah, not exactly what I'm looking for. So clearly there's a challenge here. We need some sort of basic strategy, right? So in the case of empirical adversarial collaborations, you've got a fairly well-defined strategy that people are improving upon. But what's the basic strategy for a theoretical adversarial collaboration? What can antagonists first agree upon? What's an agreed upon goal that they can set for themselves so that even if they don't end up agreeing at the end, they know that they can get a product at the end of it? So that's what I'm interested in. So that's really just background to my talk. Now I begin the talk proper, although I'm still going to try and keep it within 45 minutes.
So 1 hour, 15 minutes from now.
I've got about half an hour left. We'll see how we go. Ooh, yeah. 55 minutes, maybe. Right. Okay, so 3 goals that I'm going to set for myself that I'm going to try and achieve here. I'm going to analyze a particular theoretical adversarial collaboration that's between a philosopher and a scientist. And spoiler, I'm the philosopher. I'm then going to use it to illustrate a basic strategy that could be used as a template for future theoretical adversarial collaborations. And I mean that. I want to put forward a template that others could follow. Other theoreticians where there's no straightforward experiment that can resolve the debate. Here's a template. And even if you don't end up agreeing with each other, even if you don't like each other, follow this template, you'll get a good product out of this. And then I'll use it to argue that such collaborations are a natural place in which philosophy can have utility to science. And again, just to say one more thing about why I think this is important, why I think theoretical adversarial collaborations can advance both philosophy and more theoretical areas of science. And this was also a motivation for Ares and Latham in the 80s for the empirical adversarial collaborations, which is endless back and forth in the literature, reply, rejoinder, and depending on the discipline, this can take years. In philosophy, it can take an entire year to get a paper published. So someone puts forward some theory, some view, and someone thinks it's completely wrong. So they publish their paper, they submit their paper, and then it takes a year for that to get published. And then the author of that theory says, oh, you misinterpreted me. You didn't fully understand the theory. And so then they write there, and then it takes a year for their response. And this is not productive. This is not efficient. So for me, I think, this is one claim I'd like to make, is theoretical adversarial collaborations can make philosophy and more theoretical areas of science much more efficient. But you need a template, right? Because, yeah, okay. So first of all, here's the adversarial collaboration that I want to talk about. So I'm the philosopher, and this is the scientist. His name's Markus Müller. He's a physicist from Austria. This is funded by FQXI, or the Foundational Questions Institute. Really great organization that supports collaboration between philosophers and scientists. So they were interested in getting us to do an adversarial collaboration. There's 2 components. We split it up into 2 components. There's a theory that I developed a couple of years ago with David Chalmers. And over the summer, I went to Austria to work with Marcus, where we tried to criticize this theory. That's done. We've submitted that in this paper. If you're interested, I'm not going to talk about it today. I actually want to talk about the second one. Yeah, I want to talk about the second one for a few reasons. One is the second one is current. I'd rather talk about my work in progress. I've already completed the completed component. But also, I think the first one is a bit more relevant to the question of whether or not science has utility for philosophy. And the second one has more relevance to the question of whether or not philosophy has utility to science. So I'll just briefly mention, if you want to ask me about the completed component sometime, please do. I'd love to talk about it. But all I'm going to say about it now is it made me believe that science has great utility for philosophy. So we actually had a kind of a neutral mediator, Ian Durham, who's a physicist. That was helpful. But yeah, all I'll say is extremely helpful working with these scientists. Science definitely has utility for philosophy. Okay, with that said, I'll move on to the thing that we're working on right now, which is the critical analysis of Marcus's theory. So this is the paper that is the target. Law without law from observer states to physics via algorithmic information theory. So it's been quite a learning curve for me, because at the beginning, I didn't think I even knew what algorithmic information theory was. But it's been, yeah, certainly very interesting. So that's what I want to talk about today. Okay, 20 minutes in. So first of all, template. What are we doing? Because just to go back here, with regard to the completed component, we didn't really have any template to follow. We didn't have a strategy. We just sort of went at it. And it was nice that we came up with something. But now we're really thinking about strategy, and we actually want to write about the strategy in the paper that we're writing. so that we can tell others, hey, use this. This will accelerate progress in philosophy and in theoretical areas of science. So that's where I'm going to start. Here's the strategy that we're employing. And yeah, this is work in progress. If anyone has any thoughts on this, I'd certainly love feedback to improve this. But here's the idea. So in a theoretical adversarial collaboration, someone's theory is at issue. So in this case, it's going to be Marcus's theory. And so we've got, that's T, the theory. And so we've got a T advocate and a T critic, the advocate of the theory and the critic of the theory. Okay, so we proceed in a series of steps. Step one, just clarify what's at issue, clarify the controversial, or at least according to the critic, what are the controversial consequences of the theory, or what are the central points of disagreement. So that's just going to help zoom in, focus on something more specific. And that is, I think, what was achieved in the ENVY theoretical adversarial collaboration mentioned. They sort of got that far where they clarified the central points of disagreement, but then it kind of stopped there. So then point two, the T critic should steelman the theory. So that's a technical term in philosophy. If you don't know what steelmanning a theory or steelmanning an opponent is, it is the opposite of strawmanning a theory or strawmanning your opponent. Okay, that's more technical terminology from philosophy. Maybe that one's more familiar. Strawmanning, if you're strawmanning your opponent, what you're doing is you're objecting to their theory, but first you present a version of their theory that's totally uncharitable, and therefore makes your objections look really strong when they probably shouldn't be. Right, so the strategy is the opposite, it's to steelman. This is just a really good, I think, psychological process that the T critic should take themselves through. And time permitting, I kind of want to do that today. I would like to try and steelman Marcus. And it just really helps you get in their shoes to ensure that your objections are actually good objections and not based on misunderstanding. And so we also, perhaps we can have better terminology than this, but we call it supervised. So I'll be presenting his theory, say here, or I'll be writing that section of the paper, but it's highly supervised, because one thing that is completely banned from the final product, from the paper that we end up with, is misinterpretation and misunderstanding. At least obvious misinterpretation, not allowed. You can't have that in the final paper. And that's why this is supposed to yield accelerated progress in these fields, because there's too much of that in the literature. This can help at least reduce that significantly, I think, if it can work. So we say it's supervised. Step number three, now the T critic produces supervised objections. So here supervised means, again, objections are not based on any obvious misunderstanding or misinterpretation. So, this is too frequent in philosophy. All these papers published, objections to other people's ideas based on misinterpretation, based on misunderstanding. And then there's all these follow-up papers, and it's totally inefficient. So this is meant to be a cure for that. But it's tricky, it's subtle. This is why I use the word obvious, and I've italicized it, because that word's doing a lot of work here. Let me say something more about that after I put forward the fourth step. So step number 4, the T advocate responds and has the last word. I think that's important because it's the T advocate's theory that's on the table here. And as the critic, I'd like to think that my objections, if they really work, they're going to sort of survive whatever the T advocate ends up saying in response. But part of this is not just for us and developing our ideas, it's for the community that are interested in the relevant topic. It's to help them decide what side of the debate they should land on. So non-obvious means, misunderstandings can be corrected here if they improve how the T advocate understands or explains T. So what I mean by this is when you're in a theoretical dispute, it can kind of just go on forever where it seems like the critic is never fully understanding and the advocate is constantly trying to clarify. And given the frequency of that occurrence, how do you ever end up with a final product that you can publish that's actually productive and useful? But the idea here is the T advocate needs to make a decision about a kind of stopping point. And we think the stopping point is something like this. Okay, your objections, I still think I can respond. I still think it's because you're not fully understanding what I really had in mind, but what I have to say in response to your objections cannot be found in my written work so far. Your objections are entirely reasonable, given what I've published so far, given what I've written down. But given what I really had in mind and what I really want to say, I still think I can respond. Okay, good. Well, if I can force you to write that down clearly, that's an advance. You've advanced the development of your theory. And so you get something productive at the end of it. Okay. So that's the strategy. What I'd like to do now is maybe illustrate some of this by getting in the weeds, while also not keeping you here too long, because I know you've been here all day and are a little tired. So we'll just see how it goes. I'm going to try and keep myself, perhaps I'll go no longer than 20 more minutes, but yeah. Okay, so I'll illustrate points 1, 2, and 3. I can't illustrate 4 as Marcus is not here. And as I do this, before I get to my objections, I'm trying to steelman Marcus. I'm trying to make the theory look good. Okay, so what's the central point of disagreement between Marcus and I? Okay, start with this idea, realism. This is what I think. I'm a realist. Realism says reality fundamentally consists of an external physical world governed by simple laws. And usually these are thought of as laws of physics. Physics is what tells us what really, drives the evolution of the universe forward. Okay, so ask yourself if you're a realist based on this definition. So Marcus rejects this idea. Here's what he believes. Idealism. Reality fundamentally consists only of observer states governed by simple laws. In this case, not of physics, but of algorithmic information theory. Okay, I'll stop there because it's natural, I think, for a lot of people to look at idealism and just think, what? Realism is a very natural belief that perhaps all of you believe, I don't know. But let me just defend it a little bit here. First from a philosopher's perspective, and then second from a scientist's perspective. From a philosopher's perspective, I think every philosopher should be absolutely fascinated by Marcus's view. This idea, idealism, has had a long history in philosophy. In the early modern period, it was taken very seriously by philosophers like George Berkeley, Immanuel Kant, and then it had a lot of popularity in the 19th century. And then in the 20th century, in the early 20th century, you had various different philosophical movements like logical positivism and other movements that were really, to a large extent, aimed at refuting idealism and removing it from philosophy. And arguably, the kind of philosophy that's done today in the Western world, so-called analytic philosophy, a lot of it came out from this critique of idealism at the beginning of the 20th century and the sort of eventual advocacy, to some extent, of realism. So this idea has a long history in philosophy. Philosophers tend to think it's now been dead and buried. Well, here's a scientist that appears to be resurrecting it from the dead. From a philosopher's perspective, that's fascinating. What about from a scientist's perspective? Well, if you're a theoretical physicist or a theoretical scientist in general, you know that modern science is utterly riddled with paradoxes. There's all kinds of problems that modern science faces where it's completely unclear what the resolution is. Well, maybe, especially when you really get to the bottom of these paradoxes and really understand them, maybe there are just some really deep-seated assumptions that are giving rise to these paradoxes and preventing us from removing them. And maybe one of those deep-seated assumptions is realism. And this is really what Marcus wants to push, which is, look, here's a large bunch of paradoxes. We can actually make progress on these paradoxes if we just give up some basic assumptions and adopt a view that might seem at first unnatural, idealism. Okay, a couple of examples. The hard problem of consciousness. So this is the problem of how we are to explain how a hunk of matter like the brain, billions of interacting neurons, could give rise to anything like conscious experience. That is a major open question in modern science. Many people think unsolvable. Traditionally, the idealists thought it had a very straightforward solution. If your observer states are conscious experiences, and that's all there is to reality, there's no question of how you get consciousness from material matter, because there is no material matter. Reality is fundamentally states of consciousness. Problem removed. Okay, Marcus does not want to go that far because he's not a traditional idealist, but the thought is you could potentially make progress here. Second one, Bell's theorem undermines local quantum realism. So a lot of people look at quantum mechanics, certain results in quantum mechanics like Bell's theorem, and think, oh, so physics isn't really sort of revealing pre-existing properties of the world. And a lot of people think that a message from some of these results in quantum mechanics is that quantum mechanics itself is not really a description of reality. It more just something like encodes the credences or degrees of belief or expectations about what you'll experience after you do a certain sort of experiment. So there's at least a certain form of realism, not necessarily the one that I've defined up there, but a kind of quantum realism, realism about the quantum state, that many people think have been undermined already by quantum mechanics. That doesn't directly get you to the refutation of realism as I've defined it, and then idealism. But for Marcus, it's a route. It's at least a route there. Finally, idealism may provide the best solutions to observer paradoxes. Okay, so there's a number of things that in our paper we call observer paradoxes. These are further unsolved problems in modern science. And Marcus wants to argue that realism doesn't give good solutions to them. Idealism does. Okay, so there's a lot there. I need to narrow the focus again, keeping in mind I want to finish in 10 minutes. So,
In 10 minutes you solve this problem?
No. I'm gonna ignore. So, okay, if you want to talk about the first two anytime, please do. This is all part of the dispute. I'm going to ignore the hard problem of consciousness. I'm going to ignore quantum mechanics. I'm going to just talk about the third one. And I'm also just going to really cut down to two observer paradoxes. And the reason my choice of observer paradox are ones that I think probably you've all heard before. So hopefully the next part will be familiar to at least most of you. And they're not too hard to understand. Okay, observer paradoxes. They're paradoxes involving observers. Don't read too much into the name. But perhaps you've heard of these before, Boltzmann brains and the simulation hypothesis. I really want to focus on the Boltzmann brain paradox here, but I add the simulation paradox because it's really structurally similar and can allow us to sort of understand the view a little bit better. Boltzmann brains, what's the problem? What's a Boltzmann brain? So the problem is that plausible cosmological assumptions imply that you are probably a Boltzmann brain. And so you should expect to disintegrate any moment from now. Okay, so what's a Boltzmann brain? A Boltzmann brain is basically this random fluctuation of particles into this very complex structure, in particular a brain. But that's all it is. There's no body, it's just a brain. And it's having experiences just like yours. So you can imagine just particles in the void just coming together randomly, spontaneously creating a brain that's experiencing a room and a philosopher ranting at them, right? So that's a Boltzmann brain. Why talk about them? Well, they actually pose a bit of an issue in cosmology that hasn't been resolved yet. And this is a really nice paper that gets to the details of why we should worry about Boltzmann brains. The assumptions that go into the conclusion that you're probably a Boltzmann brain are complex, but I'll just give you the rough idea, which is that, think about the second law of thermodynamics. You have a lot of cosmological theories that predict that the universe is heading towards a state of maximum entropy, thermal equilibrium, but it will be upset every so often by random fluctuations. So the thought is that's the future. That's where the universe is heading. It's heading towards this state of maximum entropy, except it will be upset by random fluctuations of particles. Wait long enough, you'll get a little molecule. Right? Most of the time, these random fluctuations give you nothing, but wait long enough, you'll get a molecule. Wait even longer, you'll get a cell. Wait even longer, you'll get a brain. Wait even longer, you'll get this whole classroom. Wait even longer, you'll get a big bang that leads to an entire universe like this. But within that reasoning, you see the idea that Boltzmann brains are more probable than these kinds of brains, brains that are embedded in a complex environment. And so if you really think through the predictions of this theory, it's like, hold on, okay, so there are many versions of me, according to this theory, that are experiencing basically the same thing, but the vast majority of them are Boltzmann brains that are floating about in this void that are about to disintegrate. Okay, so whatever you think of this, cosmologists, many of them take this seriously, and many of them think that this has practical implications, that you should actually revise your cosmological models to avoid this conclusion that you're probably a Boltzmann brain. Okay, so that's one of the paradoxes. And again, for Marcus, it's only a problem if you're a realist. If you're an idealist, you don't have to worry about this at all. You don't need to revise your cosmological models if you're an idealist. There's no, yeah, okay, I'll get there. Okay, in the interest of time, maybe you've all heard the simulation hypothesis before. The students I know have. Plausible, structurally similar. Plausible technological assumptions imply that you are probably a computer simulation. So you should expect to be shut off any moment now. Structurally analogous because the idea is this time technological assumptions get you to this conclusion that beings like you, assuming that you are unsimulated, are outnumbered by simulated beings that from the inside can't tell whether they're simulated or unsimulated. So it's a little bit like the Boltzmann brain. They can't tell from the inside whether or not they're really surrounded by a room or they're just experiencing it. Okay, maybe you've heard of Nick Bostrom's that paper that made this famous. Again, a lot of people worry about this. Bostrom thinks there's something like a 1 in 3 chance that you're in a simulation based on good reasoning. David Chalmers just published a book saying, well, roughly it's a little less, but yeah, it's pretty substantive. Neil deGrasse Tyson gives it above 50-50 chance that you're in a simulation. Elon Musk thinks there's 1 in a billion chance that you're not a simulation. Okay, so people take this seriously. But again, if you're an idealist, just pseudo problem. Just get it. This is realism just causing more problems. Okay, now I'm going to try and explain Marcus's theory as quickly as and concisely and as clearly as I can. What are these observer states? So the idea is get out of thinking about this single objective reality that all of us observers are embedded in. Just drop that assumption just for the moment. And instead start with observers. Start with what he calls observer states. Right? We'll recover an external world approximately as an emergent phenomena later on, but we're starting with observers. That's the fundamental postulate of the theory. So Marcus says, think of everything that you as an observer perceive and remember at some given moment, something like a raw dump of all the data in your brain. We will denote this raw data by a finite string of bits. So something like x equals 0, 1, 1, 0, 1, 0. And so reality fundamentally consists of observer states encoded into finite bit strings. So the idea isn't quite that reality consists in 1s and 0s. Reality consists in observer states, but there's a one-to-one correspondence between the set of observer states and the set of finite binary strings. And that's useful because that means that we can reason about and have a science of observer states because we can have a science of bit strings. Okay, so now the laws of nature are going to apply directly to these observer states. And this was one of the, in philosophy, big traditional problem for idealism, which is if you get rid of the external world, what explains the regularities and consistencies in our experiences? And they never really gave a good answer. And what's so interesting... Sorry?
Laws of nature are theorems of arithmetic.
Are laws of nature theorems of mathematics?
Arithmetic.
Are they laws? Possibly. Here we're thinking of time evolution laws. So laws that evolve the universe forward. But this is going to be laws that evolve observer states forward and give you new experiences over time. I mean, let me just illustrate it. So here's the laws. So the universe, the observer states are not deterministic. They evolve probabilistically. And so the laws of nature here that underlie the laws of physics are these probabilistic laws. So the probability for an observer in state X to enter state Y, which I've written here as P next observer state Y given current observer state X, okay, P of Y given X is equivalent to, so this is a conditional probability, that's equivalent to what he calls the prior algorithmic probability of XY, the two bit strings together, divided by the prior probability of X. Okay, so what are these prior probabilities? We'll just take the prior probability of X. It is 1 divided by 2 to the power of L, where L is the length of the shortest computer program that produces X. Okay, so I've got a little image there of a monotone Turing machine that's producing X, and you're thinking about the shortest input, the shortest computer program that can get you that output. And that's what gives you L. And so the harder it is, the more compressible sequences of states are the more likely, according to this theory. Okay, so that's the basic idea. Now, the paper proves a whole bunch of things from this, and I'll just briefly mention these consequences. Something that he calls the emergence of an external world. So for a given observer, its states will in the long run look as if they are embedded into a larger, simple, probabilistic, computable process, a world. Okay, There's pages and pages of mathematical proofs that goes into this. He proves a number of theorems that go into this. One example is something he calls the principle of persistent regularities, where he's able to prove that given P, given how P works on sufficiently detailed observer states, on sufficiently detailed bit strings, he's able to show that if there are regularities encoded already in the bit string, then they will be seen again. These regularities will be found again. And so there's a sort of a justification for why such observers use induction to reason about the future. So he's able to sort of prove that. And so that's sort of on the road to getting the kind of an external world as emergent. You start with observer states, but you get the external world as an approximation. But of course, you only get an external world for yourself. What about everyone else? And that's the second thing, emergence of intersubjective reality. So if Alice, for example, identifies a momentary observer state in her external world, calls him Bob, then typically she can infer that Bob will approximately observe the same external world as her. So roughly the idea is this. If I can go and look at Marco's brain and really study it in great detail and sort of encode it into a bit string, then what I can do is I can, if I apply P to it, I can infer that Marco will see approximately the same world that I think he sees, the same world that I see him see it. And so we get an emergent idea of sharing a world, but it's an approximation. Fundamentally, we don't share a single objective world. These shared realities are emergent. Right. Okay, so how am I with Steelmanning? I hope I've convinced everyone of idealism, maybe not. But okay, this helps. We get rid of Boltzmann. No more, don't worry about adjusting your cosmological theories because you're worrying about the probability of being a Boltzmann brain, not an issue. The probability that you are a Boltzmann brain is given by P of X given Y. I've tried to depict it here. So on the left, that's the Boltzmann brain forming out of this random fluctuation. And there's the Boltzmann brain in the middle, thinking a philosophical thought, and then boom, it disintegrates. So X is that in-between state where things seem normal. Y is the disintegration state. And so what do we get? Well, remember what P of X means, right? And so what we're going to get is a very low conditional probability, P of Y given X, low because the sequence of observer states X, Y can only be produced by relatively very complex programs. So roughly the idea is this: if you've got X, this big bit string, and then you've got Y, this other one, the thought is, if Y were just a normal state where you just have another normal experience, it's sort of relatively predictable given the previous state. You don't need too complex of a computer program to get you that state. But to go from an ordinary observer state to a sudden disintegration, yeah, you're going to need a complex computer program to get you that sequence. And so that's what makes being a Boltzmann brain highly improbable. So no need to worry about Boltzmann brains anymore. Keep doing cosmology as you do. Don't worry if there's lots and lots of Boltzmann brains in the future. You don't have to worry about you probably being one. This is the probability that you're a Boltzmann brain. It's extremely low. Probably you're just going to keep experiencing things as normal and not disintegrate. All right, I'm very close to 45, so do I skip simulation? Probably, right? Yeah. Okay, those are the 5 propositions you need to get to the conclusion that you're probably in a simulation. I'll just say Marcus thinks basically there's a 0 probability, 0 chance that you're in a simulation, because the idea doesn't make any sense. If I try to simulate you, I don't create another conscious being. I just create another representation of your observer state. Okay, so if I look at Marco's brain right now, I've really just got a representation of his observer state. If I try and simulate him, I've got another representation of Marco's observer state. I don't duplicate observers. I duplicate representations of observers. Okay, good. So now I shift from my role as Steelmanning Marcus to criticizing. So now I play the role of the T critic. So this is step 3 in the strategy. And I guess I can more or less end with this before I have a concluding slide. Here's my objection to the whole view. Well, not the whole view, but to what he says about Boltzmann brains. It's a dilemma. Either a Boltzmann brain's observer state, so just focus on the Boltzmann brain, either a Boltzmann brain's observer state X encodes information about the environment that it's in, this maximum entropy environment, or it does not, one or the other. If it does, then I think that the probability need not be low, because X, that initial observer state, already encodes information about disintegrating. And it's got information about the environment that it's in. So it's not that incompressible that you get this next state where you do disintegrate. So it's important for him to remove that information to ensure that that information is not actually in the observer state. But then if he removes that information from the observer state, then X is going to be deficient, way too deficient for him to get any of the results that he wants. Real quick, although it's true that a Boltzmann brain can't from the inside subjectively tell that it's a Boltzmann brain, that's not enough information to go into an observer state. If it was, well, then when you fall into dreamless sleep, your observer state goes to nothing. And then when you wake up, you should have experiences that just don't correspond to your experiences from the previous day. So his observer states must be more detailed than what encodes experience. But then if it's more detailed, where does that detail come from? Well, from the rest of the brain. Oh, but what's going to be encoded in the rest of the brain is the environment that it's in. And it kind of, the reasoning seems to me to collapse. Okay, I have a bunch of objections to the simulation stuff. But perhaps you've taken in too much information already. Real quick, I'm a little bit worried about other observers, whether they even really exist, whether there's any evidence for them. Marcus is going to say, well, that's a case of the pot calling the kettle black, because realists have the problem of other minds. But I think it gets a little bit worse in the case of idealism. For example, how am I supposed to know whether or not other observer states evolve in accordance with his P? Maybe it's only mine that does. Okay, so with that said, I only went 3 minutes over what I promised. So I'll conclude. Theoretical adversarial collaborations, I think, are a natural place in which philosophy can have utility to science. I guess partly I've said a few things in that favor, and then I tried to, I guess, illustrate it by example. Maybe real quick, if you want to understand the utility of science for philosophy, one thing that you can do is ask scientists who are involved in collaborations with philosophers why. What are you getting out of this? And so just off the bat, responses from Marcus were scientists don't necessarily put much effort into the conceptual development of the theory, more effort goes into the formal development. This paper I'm criticizing is a gigantic tome of mathematics, but I think some of these more conceptual details, at least need to be tweaked. The more a scientist's work engages with fundamental issues, the more it engages with philosophical literature. Okay, I also suggested a strategy or a template. Tried to argue that our proposed strategy can be used as a template to facilitate collegial and productive engagement based on mutual understanding of goals. And then finally, idealism is an interesting hypothesis, but faces some serious conceptual challenges. And I'll end it there. Thanks for listening.